We're going to do a short unit called chemical equilibrium that will be based on a lab having to do with Le Chatelier's principle. But before we go there, let's understand what equilibrium means. In your textbook, we're working now out of chapter 18, and it stands for a state of dynamic balance. Let's start with the most famous equilibrium equation, something we call the Haber process, H-A-B-E-R. When you want to form ammonia, you can make some nitrogen react with 3 moles of hydrogen, and you'll release some energy as well as make 2 moles of NH3. That's ammonia. And if you just took some nitrogen and some hydrogen and tossed them into a container together, they would spontaneously begin to react. You could also graph the formation of the ammonia compared to the consumption of the hydrogen and the nitrogen. So the way you interpret something like this is here's time starting, and down here is that reaction coordinate or time going by. This is measuring the concentration of your reactants or products. So as you notice at the start, there is 0 ammonia. And all you have is some amount of H2 and some amount of N2. Notice they don't have to be the same amount. We usually measure those in concentrations, but it can also, if they're gases, be measured in partial pressure. Regardless, you have all reactant at the beginning and no product. Let it go, and as time goes on, the nitrogen and hydrogen get consumed. That's why these lines are dropping, and your 0 NH3 at the beginning begins to increase in concentration. And notice though, at a certain point in time, all the concentrations become constant, and that's going to happen before all of the reactants are used up. This is not a one-way street kind of reaction. This is a reversible reaction. So as I mentioned, the concentrations of the reactants will decrease gradually over time, and then they will no longer change. And that change, or that part where all the lines go flat, is at that dotted line. Notice that when we reach this dotted line, the concentrations of the original reactants aren't equal to each other, nor are they necessarily equal to the concentrations of the products. We know that those concentrations become constant because the lines become horizontal or flat. And you know that in your math class that a flat line means no further change. Notice that the concentrations are not 0 though, so not all of the reactants were converted into product. A lot of reactions do have a one-way street. They go from left to right, boom, done. None of the original reactants are present. But a lot of reactions, like this Haber process, do not go to what we call completion. They seem to stop, but they're not really stopped because in actuality, they are reversible. And a reversible reaction is one that can occur in both the forward and the reverse directions. By default, we say forward is left to right, and we'll say reverse would be right to left. Now, rather than writing these two equations, chemists will combine them and use a double arrow in between the two to show that both reactions are possible. And that is an example of a reversible equation or reaction. Which direction it goes, we're going to focus on in the lab and also when we study Le Chatelier's principle. But for right now, let's understand. I think a good analogy that I've used before is you can think of, say, a department store, and there's 50 people inside the store, and maybe in a revolving door, 15 people leave and 15 people enter. Well, if the door keeps revolving and people keep entering and leaving at the same rate, the number of people, 50, inside the store doesn't really change. So it looks like there's no change happening with the population in the store, but the door never stops spinning. So if you start a reaction like you see here, the Haber process, with just nitrogen and hydrogen present, the forward reaction is the only one that can happen, and we begin to create some NH3. Now in this diagram, you can see that the ammonia is starting to be produced, And it'll start to be produced kind of quickly as the hydrogen and the nitrogen seem to be consumed. But then the rate of the production of ammonia starts to slow down, and in fact, once you have enough ammonia present, it can spontaneously take an ammonia molecule and break it down into the original nitrogen and hydrogen. So now as soon as enough NH3 is present, the reverse reaction can occur. The forward reaction doesn't really ever stop. The reverse reaction begins, and when the two rates are equal, not the amounts, you have reached dynamic equilibrium. Equilibrium means that these opposing processes are in balance. Okay, bless me. At equilibrium, it's possible that you could have reactants dominating or products dominating, but the purpose of this slide will become more clear as we get deeper into the subject, so I'm going to let this concept of KEQ pass for now. So go ahead and fill in your PowerPoint notes if you haven't been doing so. Chemical equilibrium is a state in which the forward and reverse reactions balance each other because they take place at equal rates. Here is a lovely picture similar to what we've been doing in our lab, although it's using kind of nasty nitrogen oxide products. You can have at equilibrium, notice that we have right here, we start off with some dinitrogen tetroxide, and all you see are N2O4 molecules. But spontaneously, they can start to convert from a clear N2O4 into a brownish colored nitrogen dioxide. You might have seen these colors in lovely Los Angeles on a smoggy day in the summer, and that's that nasty sort of brownish color that the sky gets on a smoggy day. Notice that we've still got just a one-way reaction going, but what happens once enough NO2 builds up, then the brown NO2 can begin to break down, or combine with other NO2s to turn back into N2O4. I think the most important thing that you can get out of this picture is, one, you can tell by color change which way your reaction is going. As it gets more and more and more clear, you're having more of the N2O4 dominated. And as you get more and more brown, then the NO2 molecules are present in greater amounts. When a system has established equilibrium, all species are present. It's just that you might not see a clear molecule of N2O4 because it's dominated by a bunch of brown molecules of nitrogen dioxide. So very important to remember, equilibrium reactions do not stop. The rates equal each other, and all species that are written in the equation, all the reactants and all the products are present, but it's possible you could be driving more to the right, going from left to right, forward direction, or going back towards the left. The reverse reaction might be favored until a new equilibrium is established. So here are the requirements for chemical equilibrium. Has to take place in a closed system. So you noticed in that previous slide those tubes were sealed. Things can't escape and things can't enter. It's dynamic, they never stop reacting, and it only describes what appears to be in the system. It just is describing the fact that there's these two opposing chemical reactions, one being balanced by the other, and it just seems like nothing's happening, but it is. So with that, I will stop on this very short podcast, and we will look next at Le Chatelier's principle.